Let's go ahead and get started. But as we get started today, I want to let you guys know I just posted some stuff on your front page of your Canvas site. And to let you guys know so we can have more time to focus on the problems in class, I'm going to be posting some special videos of just doing the web work problems from our notes and stuff like that. And here is the web work problems from section 6.4. And as I did these particular web work problems from section 6.4, I'm sorry, 8.4, section 8.4, these web work problems, I also looked at an old final exam and pulled some series questions off of that and talked about those on this particular video. So it's actually quite nice to look at in terms of me doing the problems out of our notes and stuff, those web work problems, and a few of final exam problems on this particular section. Because right now you guys should be cranking it down. We're cranking it up more on the chapter 8 material, as well as start to getting you guys prepared for the final exam. To also start to get you guys prepared for the final exam, I also put, and I'm going to be adding to this list, but I put your first final exam information up here, and that is I've posted a spring 2017 final exam. And I also posted a Panopto video solution to the final exam of me doing the entire final exam. This is a great thing to study for, one, getting you ready for the old final exam, as well as getting you prepared for test 4. So what you should do with these old final exams to prepare for test 4 is you go through the entire exam, pull off questions from chapter 8. If it's a series or a sequence question, pull it off and analyze it and take a look at what we're doing with this stuff, and you can, fast forward and replay again those particular problems. But you should also be looking at the entire final exam. After you've done this particular exam, look at the solutions to make sure you guys are doing and making sure you got the problem right. And if you made a mistake, figure out what your mistake is. So again, here's some great stuff that I'm providing for you guys, and if you want to share it with your friends that aren't fortunate enough to be in our class, well, you're more than welcome to, but I'm giving it directly to you guys. And again, I'm going to be doing, focusing on the material in class, so I'm going to be focusing, basically posting more web work solutions from our stuff on our Canvas site. So pay attention to that. All right. Now, last time we were finishing up the sixth test. And just to remind you what it is, because it's going to play a big part on what we're going to be doing today with Power Series, but just to remind you of the ratio test. The ratio test is you have a series. It may be a general or alternating series. And what you're going to do is you're going to take the limit as n approaching infinity of the absolute value of an plus 1 over an. You're going to clean this thing up, cancel a bunch of stuff out, and you're going to get an L number. Now, first off, when do I use the ratio test? When I got one of two things. What are they? Recognition is the key. Powers of n and or factorials. When you got a series that has this in it, you want to use the ratio test. Now, once you do this limit as n approaching infinity of the absolute value of an plus 1 over an, you get L. Now here's the deal. When L is less than 1, then the series is going to converge. And if this series was an alternating series, we would call it absolute convergent. If the L value is greater than 1, then this series is going to diverge. And if the L equals 1, shame on you. You wasted your time on doing all this ratio test stuff. It was probably a much easier series. It's either a P series or something you can compare to or something like that. So basically L equals 1 says try another test, because the ratio test was not what you were supposed to use. So the last part of section 8.4 is the last test you have to memorize. Now this is an extension of the ratio test. It is test number 7 called the root test. And it's very basic, and it says this, and you can see the connection between the root test and the ratio test. You've got a series. The sum as n goes from 1 to infinity of an. It's either general or alternating series. And what you're going to do now is you're going to take the limit as n approaches infinity of the nth root of the an, the nth root of the absolute value of the sequence part of your series. And you're going to get an L number when you do this. And if L is, surprise, less than 1, then then the series is going to converge, and if it was an alternating series, it would be absolute convergent. If L is greater than 1, your series is going to diverge, and if L equals 1, you shouldn't have used the root test or the ratio test at all. It's probably a much easier test. Try another test. So look, it's the same thing as the conclusion of the root test. L less than 1, the series is going to converge. And if it's an alternating series, it's absolute convergent. If L is greater than 1, it diverges. And if L equals 1, your series, you're going to have to try another test on it. The ratio/root test was not the deal to use. Now, when am I going to use the root test? Now, this is going to be a very special case. The special case of the root test is when you happen to have a series that you have a sequence part of your series is inside of a parentheses and it's being raised to an n power. So you've got n's raised to n's. You've got a series where you have a function of n being raised to n. This is when you use the root test. Now, honestly, you can also use the ratio test on this thing, but the root test is going to be a little bit easier with that power of n aspect on it. So, here we go. Here's the sum as n goes from 1 to infinity of n squared plus 8 divided by 2n squared plus minus 3n raised to the n power. Because I have a series that has a sequence part with n's raised to the n power, n's to n's, this screams root test. So what I'm going to do here for the root test is I'm going to take the limit as n approaches infinity of the nth root of the absolute value of an. This would be the limit as n approaches infinity of the nth root of this n squared plus 8 divided by 2n squared minus 3n raised to the n power. Now, what's going to happen with this nth root of this n power? Now, officially it's absolute value, but these terms are positive anyway, so it doesn't really matter. What happens to the nth root of an n power? What do they do to each other? They're going to cancel. So the nth root and the n power cancel. This would be equal to the limit as n approaches infinity of n squared plus 8 over 2n squared minus 3n. Now, classic, take your limit as n approaches infinity. Now, you can knock yourself out. You'll get infinity over infinity. And if you want to, you can L'Hopital rule this thing a couple of times, and then you'll end up getting your answer. Or, come on, this is calculus 2. You should have the ability to look at it and tell me what the limit is. What's the limit as n approaches infinity of n squared plus 8 divided by 2n squared minus 3n? 1/2. The degree of the top is the degree of the bottom, so the answer is going to be the ratio of leading coefficients, 1/2. So my L value is equal to 1/2. Now let's apply the root test. Since L, which is equal to 1/2, is less than 1, that tells me my series, which is the sum as n goes from 1 to infinity of the parentheses, n squared plus 8 divided by 2n squared minus 3n raised to the nth power is what? L, 1/2 is less than 1. What's it going to do? It's going to converge. It's convergent. This was not an alternating series, so I would not use the word absolute convergent. We would just say convergent by the root test. Always state what test you use, statement of completion, that you actually proved this problem. This is a series that converges by the root test. Does that make sense? Now let's take a look at this next guy. I got the sum as n goes from 1 to infinity of negative n to the n divided by the natural log of n raised to the n. The first thing you'll notice is this one actually is an alternating series, because if you clean this guy up, this is the sum as n goes from 1 to infinity. Negative n raised to the n is the same thing as negative 1 to the n times n to the n divided by the natural log of n to the n. Because I've got a sequence being raised to an n power that we're summing up, making it a series here, that n on the inside with that n power on the outside, this screams root test. So I'm going to use the root test on this guy. And so this will be equal to the limit as n approaches infinity of the nth root of the an part, absolute value. This will be the limit as n approaches infinity of the nth root of the absolute value of negative 1 to the n to the n, divided by the natural log of n to the n. Now, first off, inside this radical, we have an absolute value. What does the absolute value going to do to this negative 1 to the n stuff? Absolute value is going to kill off the negative 1 to the n, because negative 1 to any power is either going to be plus or minus 1, but when you take the absolute value of that, it's going to be 1. So the absolute value kills off the negative 1 to the n. So this gives you the limit as n approaches infinity of the nth root of n to the n over the natural log of n to the n. And the nth root and the n powers are going to cancel. This leaves you with the limit as n approaches infinity of n divided by the natural log of n. Does that make sense? Now, take your limit. But this is a classic one where I can't just look at it and tell what the limit is. This is the limit as n approaches infinity of n over natural log of n. So when you plug in infinity, you'll get infinity over the natural log of infinity. The natural log of infinity is infinity, so it's infinity over infinity. So I'm going to apply my famous L'Hopital's rule to this problem. So this would be equal to the limit as n approaches infinity of, the derivative of n is 1, divided by the derivative of natural log of n is 1 over n. And what you should remember from the famous L'Hopital's rule is after you either get 0 over 0 or infinity over infinity, you take the derivative of the top, divided by the derivative of the bottom, then clean it up, and then redo the limit. When I clean this guy up, this gives you the limit as n approaches infinity of 1 over n makes it just n, invert multiply. And when you plug in infinity, you get infinity. So yes, L is equal to infinity. And the last time I checked, infinity is much bigger than 1. Therefore, I can tell you that my series, which is the sum as n goes from 1 to infinity of negative n to the n over the natural log of n to the n, is what? Divergent by the root test. So, there are 7 tests you need to know for this stuff. And this is the last one. And again, problem recognition. When will I use the root test? When I have a sequence part of a series that has n in it raised to an n power. N's raised to n's is when you use the root test. Okay? Does that make sense? So, and it's an extension of the ratio test. So there's your 7 tests. Now, as I mentioned to you guys before, you know, I'm going to do, I made a special video of me actually going through and doing all these web work problems for you guys, but I didn't want to take time in class to actually just sit there and do a bunch of homework problems for you guys, so I made a special video for it. But one other thing that I also want to put on with you guys is I also put some information about your calculator. So please read through this thing and figure out that you know that your calculator can actually do series on them, just like it does integrals, it does series. And whether you've got the old operating system or the new operating system, pretty much they're located in the same spot. And it's under the statistics. You got to go to second statistics where you go to list and choose math. And what you're going to do is you're going to sum a sequence and type it in, and you can be able to figure out using your calculator what these things can add up to be and stuff. And especially with the approximate stuff we do. So again, so I made a special video and it's posted on the first part of your Canvas page. So I'm moving on to chapter 8.5. 8.5, 8.6, and 8.7 are the last 3 sections of the series stuff. And this is the payoff. This is the most important stuff of the series. It is called power series, where we're going to be plugging x's into my series and making functions out of them. This is stuff you're going to use in differential equations. You computer science majors out there, in terms of programming, you're going to beat this stuff to death, but especially my mechanical and electrical engineers, you're going to see this series stuff at your higher level classes. And you're also going to see this material in your differential equation classes as well. So this is stuff you just can't just blow off. It's real important material. Now, hopefully you'll watch the awesome pre-section video on the section 8.5, where we have series, and the whole idea behind a power series, it's nothing but a series that has this arbitrary x in it. And the first question is going to be very simply is, okay, what values of x is going to make this series converge? You don't care about a divergent series because the thing just blows up on you. What you care about is for what values of x makes the series converge. So that's what chapter 8.5 is about, finding what we call intervals of convergence. What values of x is going to make a power series, a series with an x in it, converge. So again, I did, or Beth did, all these problems on the pre-section video. So the one thing you're going to need to know here is a little bit of the algebra review, and this is the big algebra review part that you're going to need to know. So here we go. On this algebra review, the big deal is about this: solving an absolute value less than a constant. It's basically what you got to do is you're going to have to do the double-sided inequality. It's something you learned way back in high school. Absolute value is less than c implies that negative c is less than x is less than c, and you solve for x in the middle on this double-sided inequality. So for this particular equation, the absolute value of x minus 2 is less than 10. I want you to solve for x. Well, to get rid of the absolute value, you do the double-sided inequality. Negative 10 is less than x minus 2, which is less than 10. And then you solve for x in the middle. You have to add 2 to all sides. This gives you the answer: negative 10 plus 2 is negative 8, is less than x, which is less than 12. This would be your solution. What about this one? Absolute value of 2x is less than 1. Well, again, absolute value is less than, so you do your double-sided inequality. Negative 1 is less than, drop the absolute value. 2x is less than 1. And you solve for x in the middle. You divide by 2 on all sides. This gives you negative 1/2 is less than x, which is less than 1/2. What happens if you have a power? And the power is inside your absolute value. So the first thing you want to do when you have an absolute value of x raised to a power is get rid of the power. What kills off a square? Square root. But even before you do the double-sided inequality, because you're going to have issues with taking the square root of a negative number, you get rid of the power first. So with this one, the absolute value of x squared is less than 5. You're going to go ahead and take the square root of both sides. The square root and the square cancel, so this leaves you with the absolute value of x is going to be strictly less than the square root of 5. And then, now once you got that absolute value without the power on it, then you can do your double-sided inequality. Negative the square root of 5 is less than x, which is less than the square root of 5. So, how are they going to mess you up with some of them? The absolute value of negative x squared is less than 20. Well, absolute value inside of a negative inside of an absolute value. What does an absolute value do to a negative? Cancels it out. So you can drop the negative inside of an absolute value because the absolute value kills it. So this is the absolute value of x squared is less than 20. Now we got a square, you got to kill it off. What kills off a square? Square root of both sides. So this gives you the absolute value of x is less than the square root of 20. And for those people that are in the know, what is the square root of 20? You can clean this square root up. 20 is 4 times 5, and the square root of 4 is what? 2, so it's 2 square roots of 5. So you got the absolute value of x is less than 2 square roots of 5, and then you apply your double-sided inequality to get rid of the absolute value. So negative 2 is square root of 5 is less than x, which is less than 2 square root of 5, and there's your solution. What about this guy? The absolute value of x squared divided by 7 is less than 1. Well, again, you've got a power inside of an absolute value. You got to get rid of it. What kills off a square? Square root. So take the square root of both sides. Well, the square root of 1 is going to be 1. That's fine. But the square root of x squared is going to leave you the absolute value of x. But you have to take the square root of your denominator divided by 7. That's going to be divided by the square root of 7. Because you have the square roots of a times b is the square root of a times square root of b. Square root of a divided by b is square root of a divided by the square root of b. So you got to take the square root of both the numerator and the denominator. Then you do your double-sided inequality. Negative 1 is less than x over the square root of 7, which is less than 1. Now solve for x in the middle. Multiply all sides by the square root of 7. And I end up getting negative the square root of 7 is less than x, which is less than the square root of 7. And what these things are going to end up being is my, quote, interval of convergence on what we call power series. You'll see that in just a second here. Now, definition. A power series is a series that has an x in it. So now we're looking at them as a function. A power series is a series as a function. F of x equals the sum as, and we're switching up on you guys. Pay attention to this. To make this stuff look good, we traditionally start with 0. Not always, but we like to start with the sum of 0. It just makes it look good. The sum as n goes from 0 to infinity of Cn x to the n. With summations, you plug in the first number. This time the first number is 0. That'll be C0. X to the 0 is 1, so you get C0. Plus, plug in 1, C1x to the first. Plug in 2, C2x squared. Plus, plug in 3, C3x cubed plus dot, dot, dot. Okay? An example of a particular series, a power series, is this. The sum as n goes from 1 to infinity of x to the n minus 1. When I plug in 1, 1 minus 1 is 0. X to the 0 is 1. Then I'm going to plug in 2. 2 minus 1 is 2. That'll be x plus. Plug in 3, I get x squared. Plug in 4, I get x cubed plus dot, dot. And this is a power series. Notice I got a bunch of x's in each term plus dot, dot, dot makes it a series. Okay? Now, just to remind you guys of your geometric series here, and you can actually write what we call a geometric series power series on this guy. So if you look at something like this, that problem we were just doing, the sum as n goes from 1 to infinity of x to the n minus 1, you can have A can be either numbers or x's. A would be 1, and r would actually be equal to x. And remember, on your geometric series, the absolute value of r to converge has to be less than 1. But r is equal to x, so the absolute value of x has to be less than 1. So this series, the sum as n goes from 1 to infinity of x to the n, a is 1, r is x. Since absolute value of x is less than 1, it's going to converge to our formula, a over 1 minus r. A is 1 over 1 minus r is x. So this series, sum as n goes from 1 to infinity of x to the n, actually equals 1 over 1 minus x. Okay? So, and as we write this thing out, this is what it's equal to. So now you begin to see the power of these power series. You got 1 over 1 minus x is equal to the same thing as 1 plus x squared plus x cubed plus dot, dot, an infinite series. Provided the absolute value of x is less than 1. Okay? So here, take a look at this example here. I've got the sum as n goes from 1 to infinity of x to the n divided by 9 to the n plus 1. Now this guy is special, and I'm going to put that right up here. Special. This guy is a geometric series. What was our definition of a geometric series? It is a series of nothing but numbers raised to powers of n. X is a variable, but x represents numbers. So if you look at this guy, I got the sum as n goes from 1 to infinity of x to the n divided by 9 to the n plus 1. This is a geometric series. And to remind you of your geometric series, the sum as n goes from 1 to infinity of a r to the n minus 1. And we know this thing, if converges, and we know it converges to a over 1 minus r if the absolute value of r is less than 1, and we know it diverges if the absolute value of r is greater than or equal to 1. It's the classic geometric series. Things we've have memorized. So, the question on this one is very simply this. Find the values of x that makes the series converge. Okay? And we're going to talk about something called the interval and radius of convergence here. So to make this thing converge, I'm going to make this geometric series, power series, look like the famous geometric series. So f of x is equal to the sum as n goes from 1 to infinity of. Now, on your geometric series, when you start with n equals 1, we like to have a power of n minus 1. What power do I have on this x? We have an n power. I've got too many. How many too many do I have? I got one too many. So I'm going to pull off one x. That'll be x to the n minus 1. Now look at your 9s. I got 9 to the n plus 1. Okay? I need a power of n minus 1. Again, I got too many. How many too many do I have? 2. So that'll be 9 squared times 9 to the n minus 1. So when I clean up this power series, I'm going to get the sum as n goes from 1 to infinity of x over 9 squared is 81 times, I can factor out the n minus 1, 9 over x to the n minus 1. Now, the question on this thing is very simply this. Find the values of x that the following series will converge. Now, you're in this problem, A is going to be x over 81 because it's a geometric series, but more importantly, your R is equal to x divided by 9. Now, when does a geometric series converge? A geometric series converges when? When the absolute value of R is strictly less than 1. What is R in this problem? So, the absolute value of x over 9 has got to be strictly less than 1. Does this look familiar? Solve for x. Tell me what values of x is going to make this series converge. Well, it's an absolute value less than the number. You did your double-sided inequality. -1 is less than x over 9, which is less than 1. Then you solve for x in the middle. Multiply by 9 on all sides. So you end up getting -9 is less than x, which is less than 9. This is the interval of convergence. What does that mean? That means for any value between -9 and +9, you plug in for x. This series, this power series, is going to converge. Anything beyond that, the power series is going to diverge. Now, there's one other thing. We have something called a radius of convergence. A radius of convergence is basically, it's a radius of a circle. It's the distance between the center and the outside edge. Between -9 and +9, the center would be 0. What is the distance between the middle, which is 0, and the outside edge, 9? It's going to be 9. The radius of convergence of this guy is 9. But if you want a formula, sure, I'll give you one. A radius of convergence is going to be the formula b minus a divided by 2, where a and b are your endpoints. So a would be equal to -9 on this one. B would be +9. So this will be 9 minus -9 divided by 2. 9 minus -9, 9 plus 9 is 18 divided by 2. It's 9. Now you can sit there and figure out where's the middle and figure out the distance from the middle to the outside edge. If you want to, that's fine. But sometimes this formula is quite helpful. And if your radius of convergence, if your interval of convergence is from -infinity to infinity, then you would have an infinity for a radius of convergence. That's absolutely fine. Sometimes you only have a point of convergence. Then the radius of convergence at a single point is going to be 0. Does that make sense? So, but this is what we're very interested in, and that is what values of x is going to make these power series converge. We have series with x's in them. So, now, this guy was real special. What made this guy real special? He was a geometric series. Nothing but x raised to a power of n with a constant, maybe raised to a power of n. Geometric series. Most of them aren't going to be geometric series. Most of them are going to be like this. So I have up here, the sum as n goes from 1 to infinity of x minus 3 to the n over n. And I call this guy g of x to let you know this is a functional representation. So our goal and the directions on this problem is, for all these problems, is find the interval and radius of convergence. Now, if you look at this series, forget the fact that there's an x in it. I've got a power of n in this thing. 99% of them are going to have a power of n in them. And so if I was going to use a test to try to figure out where this thing is going to converge at, guess what test I'm going to use? Ratio test. We use the ratio test when you have powers of n and or factorials. All these power series have some kind of power of n to them. So pretty much what you're going to really get into is going to be the ratio test. That first problem I did was a very special case that, yeah, I could have used a ratio test on him, but he really was a geometric series. This guy's not a geometric series. I got x minus 3 to the n over n that we're summing up. So I'm going to use the ratio test. Remind yourself of the ratio test. I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. This will be equal to the limit as n approaches infinity of the absolute value of x minus 3 to the n plus 1 over n plus 1 divided by an. Just recopy, x minus 3 to the n over n. An plus 1 over an. And you're going to keep these little absolute values in this one. Now, I also taught you guys last time about the trick of cleaning up these ratio tests. So when you clean up this guy, you're getting the absolute value of and you're going to invert multiply and group together like terms. So this numerator gives you x minus 3 to the n plus 1 divided by n plus 1. When I invert multiply, the n shows up on top, and the x minus 3 to the n stays on bottom. Now, clean it up. Your powers of n in your ratio test are going to clean up. X minus 3 to the n plus 1 cleans up to become x minus 3 times x minus 3 to the n. I pulled off one of these guys so I can get the x minus 3 to the n's to cancel. So I'm left with the limit as n approaches infinity of the absolute value of x minus 3, that would be on top, times n divided by n plus 1. Now, take your limit as n approaches infinity. When you take the limit as n approaches infinity of n divided by n plus 1, what is this thing going to go to? 1. The degree of the top is 1, the degree of the bottom is 1, L'Hopital rule it, degree of the top is 1, degree of the bottom is 1, 1 over 1. Ratio, leading coefficient, however you want to know it, that this is going to knock off to be 1. So this just leaves you with the absolute value of x minus 3. But this is the ratio test, and this guy is your L value. It is in terms of x. Now remember your ratio test. When L was less than 1, the series converges. When L is greater than 1, the series diverges. When L equals 1, you have to try another test. We want this thing to converge. So to make it converge, L has got to be less than 1. That implies that the absolute value of x minus 3 has got to be less than 1. Ratio test. L's got to be less than 1 to converge. Now we're going to solve this guy. So I did my double-sided inequality. Negative 1 is less, and drop the absolute value of x minus 3, which is less than 1, and solve for x in the middle. Add 3 to all sides. You get 2 is less than x, which is less than 4. And this is almost, gotta love that, my interval of convergence. This is almost my interval of convergence. You see, here's the problem. When you have to use the ratio test, which is 9 times out of 10 what you're going to have to do to these problems, when L equals 1, the test is inconclusive. And L is going to be equal to 1 at your endpoints. So when you use the ratio test to figure out the interval of convergence, you always have to test the endpoints. So, here we go, endpoints. What are my endpoints? So I have to test them. X is equal to what? 2. And the other one is x is equal to 4. This was your power series. The sum as n goes from 1 to infinity of x minus 3 to the n over n. So to actually test an endpoint, you've got an actual x value to plug in. So we're looking at g of 2. This will be the sum as n goes from 1 to infinity of 2 minus 3 to the n over n. Clean them up. This is the sum as n goes from 1 to infinity of 2 minus 3 is negative 1 to the n over n. Now, here comes what all that chapter 1 through chapter 8 stuff, 8.1 through chapter 8.4 stuff. What kind of test are you going to use on this dude? Look at it. Don't hurt yourselves. The sum as n goes from 1 to infinity of negative 1 to the n over n. Alternating series. So I've got to apply the alternating series test. The Bn, the part without the alternation, is 1 over n. Test it. Number 1, write out some terms. N equals 1, n equals 2, n equals 3. 1 over 1 is 1, 1 over 2, 1 over 3. Yep, my terms are decreasing. And number 2, I'm going to take the limit as n approaches infinity of the Bn, which is 1 over n. Gives you 1 over infinity, which is 0. So, my terms decrease and my limit goes to 0. What's this series going to do? Converges by the ratio, the alternating series test. Alternating series test. But most important, it converges, which means you see this point right here, x equals 2. I want this point in my interval of convergence. To show you that, I want to make that less than, or equal to. I'm going to include that particular point. Now, I got to come over here to the other endpoint. X equals 4. Plug it in, so g of 4 would be the sum as n goes from 1 to infinity of 4 minus 3 to the n over n. And you're going to catch a pattern on this stuff to help you guys out. What is 4 minus 3? 1, don't hurt yourselves, to the n over n. What is 1 to the n power? 1 to any power. What do you get? 1. So what I want you to see here is this. When you compare endpoints, traditionally what you're going to get is very close to the same series, except one side will be alternating and the other side won't be. So that's a nice way of checking your answer when you're actually doing the math on this stuff. However, this one we had to use the alternating series test because it was alternating. This one's not alternating. What test are you going to use? Well, this one doesn't require a test at all. This requires knowledge. This dude's got a name. What's the sum as n goes from 1 to infinity of 1 over n? Harmonic series. And what does the harmonic series do? It diverges, which means we do not want this point in our interval of convergence. So to actually answer the question on this problem, and it's going to be a two-part question here, and that is this. What is the interval of convergence? So the interval of convergence is going to be -2 is less than or equal to x, which is less than 4. Most of the time, we'd like you to write this answer in interval notation. Remember, bracket means include, parenthesis means exclude. So this will be bracket 2 to 4 parentheses. Does that make sense? Just getting used to both notation. The interval of convergence. By the way, what is the radius of convergence? Well, the radius convergence is nothing but a number. And the radius convergence formula is this b minus a divided by 2. So what's the distance, what's the midpoint between 2 and 4? 3. What's the distance between the midpoint 3 and the endpoint 4? 1. But I want to show you that from the formula. It's 4 minus 2. A is 2, B is 4. 4 minus 2 divided by 2. 2 over 2 equals exactly what you thought. The radius of convergence is 1. The interval of convergence is between 2 and 4, including 2, bracket 2 to 4, and open parentheses on 4, and the radius of convergence is 1. So these are the numbers you get to plug in this series. X has got to be between 2 and 4, including 2, to be able to get this series to converge. So how nasty can they make them? Well, let's take a look at this next guy. It's a power series. It's the sum. It's h of x is equal to the sum as n goes from 1 to infinity of -1 to the n times x plus 2 to the n divided by n times 2 to the n. Once again, what you will notice is all the x's have this n power to them. And basically the way to figure out the interval of convergence on a power series is you're going to use, guess which test? Ratio test. So, once again, let's apply the ratio test on this guy. It's only a very special case where you have x to the n over a number to the n, and that's all you got. We got x plus 2 to the n, we got 2 to the n, we've got this extra n stuff chunked into it as well. I'm sorry, that's not a geometric series. You got to use the ratio test on this guy. So ratio test. This will be equal to the limit as n approaches infinity of the absolute value a n plus 1. This will be -1 to the n plus 1, x plus 2 to the n plus 1, over n plus 1 times 2 to the n plus 1, divided by a(n), which is -1 to the n, x plus 2 to the n, over n times 2 to the n. This right here is an understanding algebra where it's going to help you out immensely. Because I got to clean this up. This is a big division, a(n) plus 1 over a(n). You're going to invert and multiply. But the first thing you do is you take your a(n) plus 1 and you kind of spread them out. This is -1 to the n plus 1, x plus 2 to the n plus 1, divided by n plus 1, times 2 to the n plus 1 in the denominator. Now when you invert and multiply and saving yourself time and space, the n will show up on top, grouping together like terms. The 2 to the n is going to show up on top. The -1 to the n will be on the bottom, and the x plus 2 to the n will be on the bottom. So that saves yourself lots of time and flip, multiply, and group it together like terms. Now, let's go for the jugular here. Fact of the matter is, what does an absolute value do to these -1 to the n's and n plus 1s and stuff like that? makes them positive, which means completely kills them off. Absolute value kills them off because they're sometimes negative, and that just goes away. Now, the rest of them kill off your powers. I got x plus 2 to the n plus 1. That's the same thing as x plus 2 times x plus 2 to the n. I pulled one of them off just so I can cancel the x plus 2 to the n with the x plus 2 to the n. So I'm left in the numerator with an x plus 2. I got 2 to the n divided by 2 to the n plus 1. 2 to the n plus 1 is 2 to the n times 2. The 2 to the n's cancel. So that leaves me with a 2 in the bottom. So this leaves me with, when you clean it up, and on web work when they ask you to clean it up, this is what you're going to give them. The absolute value of x plus 2 on top times n, I never touch the n's, divided by 2 is on the bottom, times n plus 1. Okay? These guys don't clean up in terms of your ratio test stuff, the n divided by n plus 1. Now, what's going to kill these guys off is now take your limit as n approaches infinity. The x plus 2 divided by 2 doesn't have an n anymore. Those guys, leave those guys alone. The n divided by n plus 1. You've seen that before. What is n divided by n plus 1 when you take the limit as n approaches infinity? 1. L'Hopital rule it, or degree of the top, degree of the bottom, your choice, but you get 1. So you're left with the absolute value of x plus 2 divided by 2. This is your L from the, quote, ratio test. Now, we're trying to figure out where this series, this power series, is going to converge. We know a power series converges via the ratio test when the L is less than 1. So L has to be less than 1 implies that the absolute value of x plus 2 divided by 2, your L value, has got to be strictly less than 1. Solving this guy, we use the double-sided inequality. Negative 1 is less than x plus 2 divided by 2, which is less than 1. Now solve for x in the middle. What's your first move? Got to get the x by himself. Multiply by 2 on all sides. This cancels. You're left with negative 2 is less than x plus 2, which is less than 1 times 2, which is 2. Then I'm going to subtract 2 from all sides. That gives me negative 4 is less than x, which is less than 0. And this is almost my interval of convergence. Last thing I got to do when I'm using the ratio test is, what do I have to do to these endpoints? Test them. So we're going to test the endpoints. Remember, h of x is equal to the sum as n goes from 1 to infinity of negative 1 to the n, x plus 2 to the n, over n times 2 to the n. So here I'm going to plug in h of negative 4. Your endpoint is x equals negative 4. So h of negative 4 is going to be the sum as n goes from 1 to infinity of negative 1 to the n, negative 4 plus 2 to the n, over n times 2 to the n. Now you got to clean this guy up. This is going to be the sum as n goes from 1 to infinity of negative 1 to the n. Negative 4 plus 2 is negative 2 to the n, over n times 2 to the n. But you'll notice inside your parentheses you got a negative. It's negative 2 to the n. Break off the negatives. So this is going to be the sum as n goes from 1 to infinity of negative 1 to the n. Negative 2 times 2, negative 2 to the n, the same thing as negative 1 to the n times 2 to the n. I factored off the negative 1 and made him his own power. Over n times 2 to the n. Now this guy, lots of stuff cancels. First off, it's pretty obvious what cancels. What cancels? To the n. But the other deal is this. What is negative 1 to the n times negative 1 to the n? They have the same power. So you can factor out that power on those negative 1s. This would be negative 1 to the n times negative 1 to the n. It's going to be negative 1 times negative 1 to the n, factoring out your power, divided by n. But what is negative 1 times negative 1? Positive 1. So this is the sum as n goes from 1 to infinity of 1 to the n over n. But what's 1, because the negatives cancel each other out, what's 1 to the n power? 1. So this is the sum as n goes from 1 to infinity of 1 over n. Well, great. Finally, all this work, at least a decent series popped out. What's this dude's name? And what does the harmonic series do? Harmonic series diverges, which means I do not want negative 4 in my interval convergence. We're not going to include that one. Then you got to do your other endpoint. My other endpoint over here is x equals 0. Plug in 0 for x. This will give you h of 0, plugging in 0 for x, which will be the sum as n goes from 1 to infinity of negative 1 to the n times 0 plus 2 to the n over n times 2 to the n. This is the sum as n goes from 1 to infinity of negative 1 to the n. 0 plus 2 is 2 to the n over n to the n. And notice the 2 to the n's cancel. This is equal to the sum as n goes from 1 to infinity of negative 1 to the n over n. Notice you get the exact same series except one side is alternating, one side's not. You never know which one's going to alternate. You got to work the problem out. But because this series is alternating, guess what test I'm going to use? Applying the alternating series test, the Bn, the part without the alternation, is 1 over n. So I got to check my two things. N equals 1, n equals 2, n equals 3. That'll be 1 over 1, 1 over 2, 1 over 3. So my terms go down. And then I got to take the limit as n approaches infinity of the Bn 1 over n. That's 1 over infinity, which is 0. The terms decrease. The limit goes to 0. Therefore, it is converging by alternating series test. So because it's converging, I want this guy. So I imply that by putting the equal into it. And this becomes my answer. The interval of convergence is between negative 4 is less than x, which is less than 0, also known as negative 4 comma 0 bracket. What would my radius of convergence be? What's the halfway between negative 4 and 0 is negative 2. What's the distance between negative 2 and 0? 2. The radius of convergence is 2. You could also use the formula on that. Does that make sense? Well, let's take a look at another one. Now these two problems right here are kind of short because I'm trying to show you guys a pattern. Here's the deal. Let's get this in your notes and get this in your brain. These are factorials. All right, this is a power series with a factorial in it. When the factorial is in the numerator, the series is going to almost always diverge. When the factorial is in the denominator, the series is going to always converge. Now, I'll prove these to you guys, but I'm going to use a ratio test. Ratio test. So I'm going to take the limit as n approaches infinity of the absolute value of an plus 1 over an. This will be equal to the limit as n approaches infinity, absolute value of n plus 1 factorial times 2x minus 1 to the n plus 1 divided by an. N factorial times 2x minus 1 to the n. Now this one's nice because there's not much to flip and multiply because you really don't even have a fraction here, but you do clean this guy up. 2x minus 1 to the n plus 1 is 2x minus 1 to the n times 2x minus 1. And the 2x minus 1's cancel. Excuse me, 2x minus 1's to the n's cancel, leaving you with a 2x minus 1 on top. So this would be equal to the limit as n approaches infinity of absolute value of n plus 1 factorial divided by n factorial times this 2x minus 1. Now let's kill off the factorials. What's the definition of factorial? This is equal to the limit as n approaches infinity of n plus 1 factorial by definition is n plus 1 times n minus 1 all the way down to 1. N factorial is n times n minus 1 times all the way down to 1. So it's n times n minus 1 all the way down to 1. Remember, it's being multiplied times 2x minus 1. Here the n's cancel, the n minus 1's cancel, everything cancels, but you're left with an n left over. So this is equal to the limit as n approaches infinity of the absolute value of n plus 1 times 2x minus 1. Now, because there's an n left over, and that's what happens with the factorials, an n's left over, plug in infinity. This will be infinity times 2x minus 1. It doesn't matter what x is. What is x times infinity? Infinity. Absolute value is going to be infinity. Your L is infinity, and that's bigger than 1, which means it almost always diverges. But here's the deal. There's always one point of convergence. There's always one point of convergence for any series. And that point is, what's 0 plus 0 plus 0 plus 0 an infinite number of times? 0. So you have, instead of an interval of convergence, you'll always have a point of convergence. And that point of convergence is what makes the series 0. So the sum as n goes from 1 to infinity of n factorial times 2x minus 1 to the n. What's going to make this factor 0? So you add up a bunch of zeros. What value of x? So the 2x minus 1 factor has to be equal to 0, so x is going to be 1/2. Your point of convergence is 1/2. And therefore, your radius of convergence. What is the radius of a single point? 0, because it's b minus a divided by 2. A half minus a half is 0 divided by 2 is 0. So you have, anytime you got divergent, there's always going to be at least one point of convergence, and that is the point that makes the series 0. Now, looking at this next guy over here, this is the same type, but notice the factorial is in the denominator. So when I used a ratio test on this one, the limit is n approaching infinity, the absolute value of x to the n plus 1 over n plus 1 factorial divided by x to the n over n factorial. When you clean it up, you get the limit as n approaches infinity of the absolute value of x to the n plus 1 times n factorial over x to the n times n plus 1 factorial. Now, in terms of canceling, x to the n plus 1 is x times x to the n, and the x to the n's cancel. N factorial is n times n minus 1 all the way down to 1. N plus 1 factorial is n plus 1 times n minus 1 all the way down to 1. The n's all the way down to 1's cancel. So you're left with the limit as n approaches infinity of the absolute value. This time the x is still on the top, but the n plus 1 is in the denominator this time. So it's the same kind of a problem in terms of cleaning it up, but when you take your limit as n approaches infinity, you're going to get the absolute value of x divided by infinity. And when the infinity is in the denominator, it doesn't matter what x is, what you're going to get? 0. And L equals 0 is always less than 1. So this means it converges always. And what does always mean? Negative infinity to infinity. This is what x can be. And your radius of convergence is going to be infinity. For this particular problem, the sum as n goes from 1 to infinity of x to the n over n. This series always converges. For all values of x, this series is going to converge. Your radius of convergence is infinity. But the trick is, when the infinity is in the top, it diverges. When the infinity is in the bottom, it's going to converge. So study hard on these power series, and we'll pick up power series representation next time.